All right, recording. All right, so today in this webinar, I'm going to cover different aspects about modeling piezoceramics in finite element simulations. My name is Hussein Shakani. I'm the founder and lead consultant of my company, Ultrasonic Advisors. Um, Piezoceramics and modeling them in FEA can be confusing because there are oftentimes a lot of missing properties. You can select different like materials. Sometimes your program will allow you to select different materials, but you're not sure if that's really congruent with the properties that you have in your actual ceramics and devices. And many times you're not really able to understand if you're doing everything correctly, because there's a lot of different kind of boundary conditions to set and polarization directions. I won't be able to get into all of the detail um, in this presentation, but I'm going to actually go into answering a very specific question. So is there anything that I didn't answer that you expected in this presentation? Please let me know, and I'll follow up with another webinar and or maybe some other resources that I can help you out with. All right. So here's a very common problem. Um, you'd like to model your piezo ceramic that you will use for prototyping. You identified such and such company that you want to purchase from, either that they're not expensive, or you can get ceramics overnight, or you have a certain supplier, but the supplier doesn't provide. Let me get this. But the supplier doesn't provide the entire data sheet. So there's I think there's 10 properties, 10 unique properties for PZT ceramics. So that's what we're going to be discussing today, not single crystal or any other type of piezo material. We're specifically discussing piezo ceramics like PZT. So their whole data sheet's not provided, or even when you purchase the material and you get it, then you don't find similar properties when you do simulations to what you measure. So what are you going to do in this case? That's actually the question that I will answer. Like, what do you do when you have difference in properties? How do you make your model or your simulated properties match that of experiments, but while following physical rules and doing things appropriately instead of just changing numbers that make things look alike and not really being consistent with what physics and the natural world has to say about how do you alter properties? Because you can do anything you want. You can do anything you want in your simulation. It doesn't mean it's correct or it's the appropriate way. So I'll describe some of the appropriate procedure, and I also want everyone to think about, because every problem is different, just to think about what the kind of the general principles of how I'm going to be describing in this specific presentation. How do you match the properties for like a piezo ceramic ring? How do you match these properties and make them compatible with your model, and what do you look for? What do you do first? Before we get into that, I'd just like to introduce my company. I provide consulting services in the area of ultrasonic transducer simulations. So if you need to get started in this area, feel free to book a call with me. I often start working with clients using a engagement or introductory engagement, which I kind of provide an overview of experimental results, some simulations, and kind of getting your team a roadmap and a clear idea of what could come next for additional work and progress and support for your project. But let's talk about the data that you need in order to model your piezo ceramic. Well, you need, and you have your, this is a charge equation. I'm not going to go into details. Hopefully everybody has at least seen such a a beautiful site as this matrices. So we have the D31, the D33, and the D15 for our unique piezo charge coefficients, and many of these are repeated. You may see in some cases where they write D32, like you may say D32. Well, for the sake of the properties, because the one direction and the two direction, they have similar properties because of the symmetry in piezo devices. 1 and 2 are the same, and 5 and 4 are also the same. So you won't see D25, you only see D15. That's to avoid repetitive writing. Although there is unique, in physical devices, there are unique directions. You can apply stress on the two, on the two direction, you could say, and you would actually have to calculate that. It's with the D15, for example. So, but in terms of representing properties, we don't repeat ourselves by saying D24 or D1 or D12. All right, just letting more people in here. So in the case with the permittivity, there are two unique directions. There's one in the thickness and one perpendicular to the polarization direction, applying the electric field. So that gives us 5 so far. And then we're going to also have, if we can go on the next slide here, then we'll also have 5 unique strain parameters. And this also, that topic that I mentioned also occurs in strain, where you don't have like a D, like you don't have a D25 or something like that. You don't have repetitive properties. You keep them the same. So also the S66 can also be represented in terms of S11 and S12, so that's also not a unique property. So that gives 5 unique parameters. And so that total is 10. So you need 10 properties to understand and to properly represent your piezo ceramic. That's a lot of properties to measure. So I'd like to just answer this question. I think this person summed it up pretty well, and they asked a question on my YouTube channel. You don't have to read all this text, but read just the bubbles, the speech bubbles. They basically received a ceramic that had different properties in the datasheet. And they also mentioned the second problem is that all the matrix tensor properties are not available. You know, if all of you in the room, and then if I were to ask, like, have you seen this problem? Everybody would like be raising their hand, and like I would see you guys nodding if you had your camera on. But this is a very typical kind of scenario, and we have, a lot of times you have standard properties in your data sheet, or even within your simulation program, but you want those to reflect more closely the ceramic you will actually use. So how do you know that your ceramic has different properties? How do you know that? So, well, you measure your as you guys all pretty probably know, you measure your impedance response, and in this case, I'm measuring for this ring here. I'll show the next slide. So we have this ring. It's 50 millimeters diameter, and you know the simulated properties, what you would input to your simulation from the datasheet will not match what you actually are measuring. So this is a discrepancy. You'd obviously like that to be reduced or eliminated as much as possible in order to be confident in the modeling that you're going to do for your prototype, that your devices that you're going to develop. So you see discrepancies in the low frequency response. Here I did 4 kilohertz to 6 kilohertz. You see that the simulation has a higher permittivity, or a higher capacitance, basically due to lower impedance. You also find that this first resonant mode at 36 kilohertz approximately, the experiment has a higher resonant frequency, which means it's apparently more stiff than what the simulation is saying. And there's another resonant frequency here at about 110 kilohertz, which also shows a higher a higher stiffness for the experiment in terms of having a higher resonant frequency. So how do you kind of logically go ahead and match this all up, without like kind of fooling yourself as to what you can actually do and what you can actually change? Like, how do you like put everything together without breaking something? And so I guess that's the question of the hour, and that's what I'll aim to answer. And if I miss anything in describing this, yeah, definitely definitely let me know. And I see there's kind of some activity with a suggestion in the chat. So yeah. So I'm going to describe the simulation setup just because it's important to go over. So I had this disk. I also had this. I have this like kind of test holder. One thing I did, because this is a high Q material, a PZT8, once I loaded the ceramic in, I unscrewed the knob in the back, which kind of holds it all, which kind of keeps those springs stiff, so it loosened that stiffness, so it allows the ceramic to vibrate even more to actually measure the appropriate quality factor. A lot of times these holders constrain the ceramic way too much, and you end up getting a really low Q for a really high Q material, and it kind of baffles people, and they maybe call the manufacturer and say something's wrong. And the actual measurement technique is very important, especially when you're thinking about putting these in FEA. If your measurement technique is not right, then you will end up with properties that don't physically meet each other. They don't make sense together because the measurement was incorrect. So that's that. So the essential point, and I'm actually going to jump into the finite element model here because I can. But I'm just going to show how I set it up, just in case there are any questions later. There will be no questions as to how things were made. So it might be small on your screen to see, but some of you may be familiar with COMSOL. The first thing I did was create this disk in a CAD program and then import it as a step file. Then and then after doing that, then I assign the material as PZT8. So there is a PZT8 standard material, and today I just use that standard material to base my for my starting point for my optimization. You can use the other thing that you can do instead of using your simulation standard material for starting that optimization process to get it to look like your experiment. Instead of using that, you can also use your find another data sheet from a different manufacturer, albeit, but it has the full data, all the 10 constants for you to model off of. So if you find a PZT8 material with these 10 constants modeled and represented, given to you, even if it's of a different manufacturer, it can be a good starting point for you to get as close as possible before you start shifting and changing things. You don't want to start with the PZT5 to get closer to a PZT8. Now you won't be too far off once you modify all the properties, but it's like you ought to start as close as possible. If you're starting from PZT4, then you start from that point too, and when you find a similar material. Another thing here is I always use strain charge. I never use stress charge. Strain charge, if you don't know what I'm talking about, then just remember to use strain charge when representing your properties. You have an ability to select which kind of properties you want to use in COMSOL. So and I think in other simulation programs too. The strain charge uses the piezoelectric D coefficient. The stress charge uses the E. Basically, the D coefficient is going to be the D coefficient is more it's more easily measured, and it's more closer to what you're going to be doing in your experimental results. So that's what I use. And it's also the stress charge uses the permittivity under constant strain, which doesn't really exist. So in reality, so it's like you're using kind of morphed forms of representation of the material. So just use strain charge, and I think it's it just works out a whole lot better when you're shifting these properties to know that. So the PZT material is automatically shown. So here's the strain charge. This is where you choose it. When you choose your piezo material, you choose strain charge from this area there. You have to put damping. So you left click and you put damping. And I showed an equation here. Okay, I showed an equation. There's an equation right here just showing how you get and arrive at that damping value from your quality factor. And it's on this it's on this article that I have, so you can reference that article. You can search for it on Google, and it'll show up. Impedance frequency response, Ultrasonic Advisors. If you Google that, it'll be the first kind of hit there. So you're actually able to calculate isotropic loss factor. Now, loss factors are not isotropic. Every single elastic compliance value, all the 5, have their own loss factors associated with it. It's too cumbersome to calculate all of that, and loss factors very much change in experiments a huge amount, especially in comparison to the real properties. So you ought to just put something close and have one value and make life simple, instead of kind of go for a matrix. Like, just don't do that. Just go for a single value, and there's an equation to convert from like 1/2q is equal to this eta loss factor, and I make it isotropic. So in terms of assigning basic electrostatics, you get to assign one side to the ground, one side to the one side to the 1 volt to the top, and also the polarization is automatically defined to be in the Z direction, so I don't have to assign a polarization direction. That could be a tricky point if you import CAD and somehow it's tilted, and then you just put piezoelectricity on it. If this was actually pointed up as Y instead of Z, then we would actually be shear, it would cause shear because we're now applying our voltage perpendicular to the polarization direction, and that's why it's really important to verify some of these properties. Like, for example, verify that your capacitance or your impedance actually matches the capacitance expected by the permittivity in the 3-3 direction. Like, verifying that's really important, because you can make a simple mistake like having this as Y and not realizing that, and you maybe even do a lot of results and based off of that work, and it ends up all being wrong. That very much could happen. So we got ground. The other thing we have to do is in COMSOL, there's no button to get impedance plots. Like, you can't just left click plot impedance. You have to do it manually, which is kind of cool. I think in ANSYS there's a button to do it, but how it works and how correct it is, it's up to you to decide. I like to do it manually and know what's going on. So I basically said integrate the charge on this face. So I'm actually measuring the charge as it's going to oscillate as I'm sweeping frequency. It's going to I'm going to be able to get the charge. This is what this expression is, and it integrates the charge density, which gives you charge. And obviously charge times frequency, that is amps. And if you know the voltage, you can get ohms. And all of this is actually outlined. I have these 3 frequency regimes. I have 1 low frequency for capacitance type of behavior, and 2 resonances, like one at 30 kilohertz and one like 110 kilohertz. And I solve, and my solution, I actually have to write my own equation in order to develop impedance. That's voltage divided by the absolute value of the boundary probe, because if the charge also has real and imaginary components, because this is a frequency domain problem, so you have to take the absolute value of that multiplied by the angular frequency, and that gives you impedance, and you can kind of see this 3 regions occurring there. So that's how you set up the model. And that's the modeling I used. And when I'm talking about altering material properties, I went here in this area and altered the properties there in order to achieve the results that I'm going to be showing. So hopefully all of that is clear. And that's how I generated these plots as well. All right, so let's get started and kind of go and try to understand the differences in how we go forward. So we have these 10 properties. We want to get which 10 of these 10 properties are the equivalent of that to our actual ring. So you could have started from an example material. You could have started from a partial data sheet. I didn't exactly outline the method to use a partial data sheet, but it's similar concept of using comparisons, but you don't have experimental values. So we have this full data there for the standard material library. And this is, again, PZT8. We don't want to choose a PZT5 to get to a PZT8 disk. So the first thing we do is that you look at the important parameters between your experiment and your base simulation. So first is the off-resonance impedance. This is going to be used to get your permittivity in the 3-3 direction. So we log those 2 values, 5 kilohertz experiment, 5 kilohertz simulation. Then we look at the first resonant frequency, resonance and anti-resonance, the frequency difference. I'm not calculating coupling factor because we're not really comparing large differences in frequency. So this is effectively the coupling factor, the difference between the frequencies of resonance and anti-resonance. That's what I'm using as a instead of doing a square root value 1 over this squared. You don't need it doesn't provide much more value to do that. And also did the second resonant frequency, and I'm going to describe why I'm doing these first 2 resonances instead of focusing just on one. And also, you might be wondering, this disk is used in the thickness direction. It's used in the 3-3 direction. It's not used radially. These are low frequency modes. You may be wondering why is he analyzing low frequency modes in order to, or radial modes or planar modes in order to understand and use a device in the thickness, or the, that's not the thickness, it's a 3 direction. So there are a couple of reasons for doing that, both practically experimentally, but also we'll end up using these values to end up calculating those properties which are going to be relevant for our thickness, for our 3 direction properties. So we're going to start with the approach of using the planar properties, but we will end up calculating the thickness properties in the end. You can't exactly jump to the thickness because the disk is the thickness mode. This is a kind of a subtle point, but it's important that the thickness mode is not the K33 mode. The thickness mode has kind of officially different boundary conditions, which effectively constrain your ceramic as it oscillates on the edges due to basically kind of momentum. So that ends up being a different problem, or a different type of device altogether, and it's also usually very high in frequency, which does also cause problems. These frequencies are similar to the operation, like 30 kilohertz or even 110 kilohertz might be similar to an application you may have a piezo ring installed in. So first resonance, second resonance, also the frequency difference and the ratio as well between them. So I mentioned before, we already talked about losses, but the losses are they're the easiest thing to get 100% right, because the losses don't depend on any other property. They're not codependent. You can do the quality factor, and that is the loss. Although but it's the hardest thing to get right because it keeps changing for high Q materials. Every time you put it in the sample holder, it's going to change. Like it changes from 1,000 to 1,400 to 1,800, and it kind of just shifts back and forth. The higher the Q, the worse it is. And it's also hard to get correct because it varies when you get into your final experiments, where you have interfaces which really lower the Q of your final device. It's it kind of doesn't become as relevant whatever the Q of the ceramic was once you put it all together. So it's also the hardest thing to get exactly right. So you can, and basically the number of frequency steps you need to use if you have a really sharp peak or a sharp impedance dip due to having a high Q, it's like you have to put all these frequency steps in there. You can avoid that problem by increasing your Q, decreasing your Q by a factor of 10, or increasing your losses by a factor of 10. But then you'd have to remember when you do care about the amplitude, that you have to kind of recalculate what the amplitude would be, and you can use a version of the 3 dB bandwidth. Instead of calculating the 3 dB bandwidth, you calculate you then extrapolate. Well, if the Q is 10 times higher, how much higher would the displacement be based off a 3 dB bandwidth of the existing data? That's a kind of a trick you could do if you don't want to put all these frequency steps and you have a high Q device. But in the end, usually devices aren't more than 500 quality factor, especially at higher power. So it's practically not too much of a problem, but it can be theoretically a problem if you go from with straight PZT 8 properties. But just again, you have to put losses, like put some losses there. A Q of 500 is good, like 0.001. That works well, like I have in this example there. All right. So the easiest thing to fix in the simulation and experiments is to get the permittivity correct. It's also a property which is independent of others. The permittivity under constant stress in the 3 direction. So there's a question for the experiment, especially the second radial mode. There exists a nodal circle. Does the results change if you held it at a nodal point versus a non-nodal point? So you'll know if you're really damping your material if the Q factor is low. So if you maintain like a Q factor over 1,000, then you are not gripping it really tightly. So so if you have a Q factor over 1,000 for like a PZT8 material, or even over 700, then you will not be it is not being damped. At least the resonant frequency is not really being affected by how you hold it. So that's what the case was my case. I think the lower frequency was, I think 1400 Q, and the higher one was 1800. Was what I measured. So I was pretty confident for my results that I was not damping, and that's why I even mentioned like I unscrewed that just to give it like just to unconstrained as much as possible. But yes, in general, you want to hold things on the nodal point if you can, if the nodal point exists on in a plane that you can hold it. That sample was a bit awkward and big for my results. And also, oh yeah, another note on sample measurement of Q. The bigger sample you have, the easier it'll be to measure a higher Q, because the little tiny place you hold it is actually tiny in comparison to the entire ring. The smaller the ring, the more likelihood that you'll be damping it the way you hold it. But yeah, I would recommend maybe you can do the experiment more than once, try and see how stable your results are. But so back to the topic. So the permittivity is the height of the impedance curve. It also relates to the capacitance. It's easy to correct for. It also strongly affects the coupling factor. So if you change the permittivity, you change the anti-resonance point. Like this is a high, normal coupling factor, but then when you change the permittivity, you make it larger, your coupling factor gets smaller, and the resonance and anti-resonance get closer together. Or actually the anti-resonance just drops back. Resonance stays put because it's only dependent on your elastic compliance. So you basically get a ratio of the two, and you can increase your permittivity or decrease it in this case in order to match your device. So basically now the simulation is going to increase. If you decrease the permittivity, the impedance will increase, and these two lines will become right on top of each other, and that's what we want. Get some water. Okay. So this permittivity, in the one direction perpendicular, should also be changed, but we're going to get to that in a second. You don't just change it with the comparison. We do, but we'll save that to the end, and for a good reason. So compliance, let's do that. The elastic properties. So the disk, like a solid disk, is very similar to a ring, and in a disk, the first and second resonant frequencies depend on both S11 and S12 both. And studying the equations that are there for a disk, and I go over that in one of my videos. How do you calculate properties for a disk, and what are the equations? But the basic rule is that when the ratio between the second resonant and the first resonant frequency increases, you also have an increase in the ratio between the S12 and the S11. So we find that the ratios are actually very similar for both simulations and experiments, so we don't need to vary the ratio between these two properties. We should increase them equally or decrease them equally when we want to affect the resonant frequency. I hope you guys can understand this point. Let me know if you can't. I can circle back to it now or even at the end. But this is a subtle point that you get from understanding characterization and how you characterize properties. So it's also helpful to understand theory when you are in the simulation venture. It's not simply just about plugging in properties and getting out values. There is, and when you're missing results, then you kind of need to flex some theoretical muscle in order to cover the gaps. So the simulation has too low resonant frequency, therefore I need to decrease the compliance. So compliance is like softness. So basically you're making it stiffer, therefore you're increasing the resonant frequency. So I decrease both of them by the same amount. And in COMSOL, there's this S22, which you also have to populate. Remember, S22 is just S11, so you have to re-put that in again. So be careful when you're using COMSOL and even other programs where there are redundant properties measured like S22. Some piezo-specific programs don't make you do that, but COMSOL does. Because in general, let's say if you had a composite or something, you could have a different S22 than S11 in different directions, like looking outward this way and like this way. So make sure you populate all those. So then you log the important parameters and how they changed. Obviously, as I mentioned, the permittivity pretty much matches exactly because it's kind of independent of everything else, but it does affect anti-resonant frequency. So when we decrease the permittivity, we popped up the coupling factor, because now it says, hey, low permittivity, same charge coefficient. Oh, the coupling factor must be higher, and indeed it does kind of go higher at that point. It's a little bit too high. The resonant frequency has increased, but it's still too low. That's why I put it in red. The anti-resonant frequency is lower, but it's still, the frequency difference is not acceptable at this point. The second resonant frequency is still low. We don't precisely need to be still analyzing this anymore, but I'll just continue to look at it. And the frequency difference does show that it has too high of a coupling factor, because the frequency difference is too high between these two, between the resonance and anti-resonance. So we got more work to do. We're going to decrease the coupling factor further. Decrease the compliance further. Okay, so coupling factor is too high, frequency is too low. Decrease S12 and S11, and also decrease D31 and D32. Like, D32 is not a unique value, it's the same exact thing, but you have to put it in again in COMSOL. Or you're going to end up with some kind of strange anisotropic device. So still, like, the frequency is too low. It did increase. The coupling factor, I don't know if it increased or not. It decreased slightly because I decreased the charge coefficient. So I'm just continuing. We continue on this process, and you can kind of get the drift here. Like, whenever I want the coupling factor to change, I change the D coefficient. Whenever I want the frequency to change, I change the S, the compliance, and I just rerun that, and then I rerun it, and it kind of seemed okay. I'm not going for perfection at this point. I don't think you should either. So then these values end up being similar. So if you saw how I started permittivity, then I went to compliance, and then I went to charge coefficient, and then I kind of iterated on compliance and charge coefficient, and until I got the values. And this resonant mode, obviously, the planar mode is D31 and S11 and S12. S11 and S12 just represents the Poisson's ratio, the S12 ratio to the S11. So that's why it's like a planar, and it all works out, and it makes sense. That's the point. Like, we're doing a process, and we're optimizing in it with the process, which makes sense. Okay, so this is what we got so far. We got all these green, which are calculated from experiments. This is calculated from experiments, D31, D13 by matching. And then for the rest of these yellow parts, we use ratios. So we find the ratio between S11, between COMSOL and the ring new properties, and then we use that to we use ratios to calculate the new S33, the S55, and we do the same thing for the permittivity. But we don't do that for D33 and D15. You're not just going to use a ratio, and I will explain why you don't use a ratio for these properties, because you might make nonsensical, non-physical properties. You might be tempted to put that in. So you use the coupling factor comparison to compute, and I'll explain what the coupling factor comparison is. From the new properties that we just calculated from our optimized model, we have a K31 coefficient of 0.28. So we have the coupling factor for the D31 mode is 0.28. So we have to note that the original COMSOL values gave a coupling factor of 0.34 for the same mode type. That's important to note, because this guy has lower piezo coupling, likely a lower spontaneous polarization. Everything that's included in that has a lower polarization, or has lower coupling factor than the COMSOL. So we have to adjust all the coupling factors. So the coupling factor of the K15 is likely to be lower, and the coupling factor of the K33 is likely to be lower. And you kind of see how we're now bringing in the physical reality of how this is not as optimized of a material as the original starting standard library material. So we have got to account for that. So here are all the COMSOL values that I calculated from the standard definitions of these coupling of these specific modes of the K15, K33, and K31. I came up with the ratio between the K31 and the K31 standard, the experiment and the standard, and I saw that, well, the new values are 92% of the old one. So there's a reduction in the coupling factor, and I applied that reduction across the board. Obviously, we already knew the one for K31, that was our experimentally optimized one. But then in order to jump to the K15 and the K33, we have to use that factor. And that's one of the key points here that you may not have realized by yourself, and that's hopefully why you're on the webinar, is to kind of learn about these specific things that aren't obvious to ensure that you have a physically compliant you followed a logical process instead of just using a process of comparisons, or just trying to get everything to match up correctly. You follow a good process, you get close enough, then you're good to go, I think, for your next step. That's what I say. So then from that point, once we have our K15 and K33, then we can use the same definition to calculate the D15 and the D33. So I calculated D15 to be 260 and the D33 to be 182 from this method, from this new lower coupling factor. Hope that makes sense. This coupling factor, and these slides will be sent out so you can kind of follow along in the process too. And hopefully you might even be able to do you might even be able to use COMSOL. If you have COMSOL, you can use the slides and you can use the calculations and follow through if you want to do it yourself. So now here we go. So now we've used the coupling factor comparisons to compute. We've had experiments, we've had comparisons in the yellow, and we've had the coupling factor comparison in the purple. So here are some of the topics I didn't cover. I think it was actually getting kind of long. There was about 41 slides, and I was not stopping anytime soon. So I decided just to cover this one aspect of getting from standard library properties to your custom properties for your disk that are much closer, and you followed a reasonable process to get there instead of just kind of guessing and putting stuff in, which never feels good to an engineer, just like randomly shooting in the dark. So I didn't discuss how to use a partial data sheet. Like if you don't have the material to test, but you still want to simulate how that would behave. But the process is sort of similar to what I did here. There are comparisons, there are coupling factor conservations. You do need a standard. You do need an example of a fully populated material data sheet in order to get to that to get to an equivalent version of an estimation for your new material that you don't have. I didn't discuss how to verify piezo physics correctly, but basically you do some of the basic property definitions like you would in real life. You apply a force, you measure the charge. You apply a force, you measure the displacement. You apply a alternating voltage like in frequency domain, and you make sure the capacitance makes sense with the permittivity you put in to ensure that you don't kind of like mess up the polarization direction. But hopefully you can find that to be an important way to verify. I sometimes find engineers just going straight to mechanical analysis, like we put in voltage, we get out displacement, but just completely ignore the middle part, which tells you if the equation actually made sense. I understand that displacement is what you apply voltage for. You don't apply voltage to get current, but what the current tells you is a lot of what's happening in the piezo device, and also it tells you a lot of mechanical information, which is very easily relatable to experiments, which is why it's one of the reasons why it's so important. I didn't discuss simplified representation, but I did that in the first webinar on modal analysis because I used a program that doesn't have isotropic. But basically, you assume isotropic material properties in the property direction you care about, like the 3-3 direction, and then you apply Poisson's ratio, and you're good to go there. I didn't discuss some major pitfalls, but one major pitfall I'd like to discuss explicitly, and I've seen this multiple times actually, is when researchers or engineers are trying to compare displacements between experiments and simulations, their first desire is to either change the D33 coefficient to make it match how high the experiments are going, or the displacement of the experiments, or they're changing the loss factor to decrease or increase the displacement. The actual thing is that the loss factor is independent of everything because you can directly calculate it from the bandwidth. So that's something to note, that when you're doing like displacement matching, use the loss factor from the bandwidth first, then screw on with the kind of electromechanical properties. That's just one kind of thing I wanted to make sure that I mentioned. So we're almost finished here. So all the tensor properties are are rarely given, and they're not really reliable either because they take, I think, 4 different types of PZT materials shapes in order to develop enough different types of resonance to determine the properties. Each of these materials are made from different materials, so they may have property variation, as well as the fact that they're made differently, polarized differently, that they will have different properties and results. So you're basically getting 4 different material samples with different properties to make a property of one material. That's why there is some research on getting all of the properties from a single sample, like a cube or something, to make it all relevant and reliable. But that's not really accessible to the masses. This is the traditional ways to use multiple types of resonant structures in order to formally get all these properties experimentally, which is kind of it's an overdue, and it has some issues using all the types of resonance. It's all many types of experimental samples to do that, and it's not really practical, and it's going to take forever. So FEA can be matched to experiments, but the results should be consistent with the quality coupling factor, like I mentioned, in order to avoid making a fictitious material or having too high of a D coefficient. Nonlinearities may void the possibility of a perfect match. Even frequency dependence of properties, of capacitance, of losses. The whole, like one person was mentioning, the whole, how you hold the ceramic may affect one frequency versus another differently. So there are nonlinearities, although we do treat our piezos, especially in the analysis I did, it's all linear. But when real life deviates from linear, that's where FEA kind of gets tricky as to what you need to pay attention to and what you can kind of skip over and say that this is experiments. Also remember that the prototypes will show differences from the ceramic simulations because of interfaces that exist in prototypes that don't exist when you're just doing ceramics. PZT ceramics have inherent variability, so you can't have a model for every type of material. There'll be some variability, but hopefully you made your design such that that is not a huge issue. And also the point of FEA is to make intelligent prototypes, not at perfect simulations. So really ask yourself, well, am I doing enough? Did I follow the right procedure? Do my properties make physical sense? Then if the answer is all yes, then I think you can kind of go forward and iterate on your prototypes before trying to get a perfect simulation in order. And sometimes I even recommend just don't even worry about frequency analysis, just do modal analysis because the information is not too much more valuable and you need to get to your prototypes. So I just want to put a plug in here as why you might choose me for your prototypes. For your simulations. So I can help you evaluate an existing model, understand the relationship between, I have a deep understanding between experiments and simulations. Also the areas of unnecessary complexity, which really bog down many FEA projects, which I'm able to kind of cut through pretty easily. Modeling for the goal, not just the numbers, having a physically correct model instead of kind of one that you populate properties or conditions that you're not really sure about. Well, you don't want your team to get all the way up to speed and become experts in this area. You'd rather already hire someone who is an expert. Simulations will reduce your prototype time, and it'll also work alongside of your prototypes, and it kind of won't slow that process down. So if you want to talk to me more about how I can help you in simulations, perhaps do that introductory offer if you have a company and you're looking into simulations or you want some help, that would be a great way to do that. So I will now stop the recording.